Hello. Today we're going to discuss the metric tensor and parallel transport in curved manifolds. In essence, these are two ways to describe the space-time metric or the space-time manifold, or a way to describe the curvature. At least this is a beginning point. So first we're going to start with asking the question, what is a metric? Last time we saw that the metric is intimately related to the definition of the dot product. So A dot B is equal to the tensor G, and we're going to give it two arguments, A and B. And we found that in component notation, this was G alpha beta, A alpha, B beta, and we said that G alpha beta is equal to the components of the metric. I'm going to go ahead and use this same definition to show that the metric also gives us a way to define links. So for example, if we have some infinitesimal vector dx, which is meant to represent the disk or a vector that connects two points in space, then the magnitude of that vector is given by this. Well, this is just equal to dx comma dx. We're supplying dx to each argument of G. And I'm going to restrict this conversation to the spatial coordinates right now, and we're going to ignore the time coordinate. And so we're going to use just Roman indices. And this is Gij dx I dxj. And we're going to call this ds squared. So where ds is meant to represent the magnitude of this dx. In relativity, we call this the interval. And it is invariant. Now, the interval has slightly different behavior than what you're used to in just space. When you include both time and space, and you include Einstein's postulates, one, relativity, and two, that the speed of light is the same no matter who is observing it, then this ds squared has some odd behaviors. For example, it can be 0 or it can be less than 1. But for now, let's just stick to your intuition, and let's just consider dx to be a vector within space alone. Okay. Now we see that ds squared is equal to Gij dxi and dxj. Well, you may know from Pythagorean theorem, ds squared is dx squared plus dy squared plus dz squared. And from this, so this is in Cartesian coordinates. In Cartesian coordinates. And if you know the interval in this way, then you can, just by looking at the interval, you can inspect what is the metric. Apparently there are no cross terms. So there are no terms where I and j are not equal one another. Otherwise, you would have a term like dx dy, but we don't, or dx dz, but we don't have any of those. So the only terms in the metric are ones in which I and j equal one another. So g, I, j. Now these are components of a tensor. If I want to write this as a matrix, remember a matrix is not the same thing as a tensor, but I can represent the components of the tensor in matrix form. Then when I is equal to 1, then this is the coefficient in front of dx squared is 1. When I and j are equal to 2, then once again, we have 1 in front of dy squared. And when I and j are equal to 3, we have 1 in front of dz squared. And there are zeros otherwise, because there are no cross terms in this. So this is the metric. And we can also write this as, since these are ones, if I and j are equal, but 0 otherwise, this is delta, whoops. This is delta I, j. Now notice, one might call this the Kronecker delta, but this is a specific kind of Kronecker delta. This is one in which I and j are downstairs. In other words, this represents a covariant tensor. This delta ij is a covariant tensor. We'll see other versions of this later. Okay, so if there were cross terms, once again, if there are cross terms, then we might have something like ds squared is equal to dx squared plus 2dx dy plus dy squared plus dz squared. And I'll leave it as an exercise for you to infer what the what the metric would be that you would infer from that. Okay, now moving right along, if we recall, last time I introduced that to find the components of Gij, this is equal to the tensor and passing it the argument of the basis set in each of the arguments. And once again, this equals to ei dot ej. So those are 3 ways to represent the components of the tensor, of the metric. And this is general. If you have some other coordinate system, let's say, for example, spherical coordinates, then you can find the metric tensor for that other coordinate system like spherical coordinates. Now let's go ahead and use this. We're gonna, once again, by inspection, figure out what is the metric tensors for spherical coordinates. I happen to know that the line interval ds squared using Pythagorean theorem once again is dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared, where this time 1 corresponds to r, 2 corresponds to theta, and 3 corresponds to phi. All right, and just by inspection, I see that the metric is the coefficient in front of dr squared is 1, and then there are no off-diagonal terms. All right, and then 0. And then coefficient in front of d theta squared is r squared, and no off-diagonal terms, and then 0, 0. And then the coefficient in front of the last one is r squared sine squared theta. So that is the metric for spherical coordinates. If you know, last time we also introduced how do you transform a covariant tensor, a rank 2 covariant tensor to another. And so I'll just write that down again to show how you can find the metric if you know another metric. So for example, G, and let's use K and M. So we're going to stay in spatial coordinates once again, is equal to, we're going to write this in terms of Gij. Okay, and I know it's going to involve these capital lambdas. And once again, lambda will fill in the indices in a second, represents the derivative of one coordinate with respect to another, and we're going to fill in the indices. And each of these is a different, the one at the top is one coordinate system, one at the bottom is another coordinate system. All right, so let's fill this in. So I know that on the left-hand side, there is no I and J, and on the right-hand side, there is an I and J. So that tells me that we're going to need to contract over both I and J. So in upstairs in each of these, there's going to be an I, and make this K, and then upstairs of this one is J, and we'll make this one M. All right, so now I'll go ahead and fill in just to complete the definition. We have I, K, and we have I, K. And in this case, I and J might represent the Cartesian coordinate system, and K and M represent the spherical coordinate system. And so we can express the spherical metric in terms of the Cartesian metric. And since the Cartesian metric is simply the Kronecker delta, this is a very useful expression to find the metric of any coordinate system starting with the Cartesian coordinate system. If you start with the Cartesian coordinate system, you can derive what is the metric in any other coordinate system, as long as you know this, you know the relationship between the Cartesian and that other coordinate system.